Today we're going to discuss the microanatomy of the kidney, the nephron, the collecting ducts. We'll talk about the steps of urine formation, and then we're going to go into more details about glomerular filtration, including the GFR, the glomerular filtration rate, and NFP, the net filtration pressure. All right, so we're going to start off with a quick and dirty sketch of the kidneys and the renal pyramids, the medullary pyramids there in the medulla of the kidneys. And of course the outer part is the cortex. Today we're going to be emphasizing the idea that there's going to be a blood supply coming into the hilum through the renal artery, and of course leaving through the renal vein. And that kind of starts the whole ball rolling. About 20% of your cardiac output actually is filtered by the kidneys each minute, so it's helpful to look at the blood supply. And of course we have the ureter there that conveys urine, which we're going to be drawing in orange today, which is the end result of filtrate that is produced by these stripes here called the collecting ducts. So the collecting ducts are going to be producing a substance called filtrate, which once it leaves out of the collecting ducts and becomes part of the minor calyx, major calyx, renal, pelvis, and then the ureter is then urine. And that is technically outside of the body. So we are going to be watching that theme now, and we're going to start off by drawing a glomerulus. We start off with the afferent and the efferent arterioles. The afferent arterial is thicker and the efferent arterial is thinner. And just kind of a little bundle of blood vessels there, kind of uniting them. That bundle of blood vessels is called the glomerulus. And the glomerulus is going to be surrounded pretty tightly, with just a little bit of space in between, by a glomerular capsule. It used to be called the Bowman's capsule, but we are changing some of the terminology in anatomy. So the glomerular capsule surrounds the glomerulus and basically captures the filtrate as it is pushed or pressed out of the glomerulus. That is how your blood is filtered in the kidneys, basically. That's the start of it. So after the glomerular capsule, we start into a tubule system. The first part of it is called the proximal convoluted tubule, or the PCT. And then we have the nephron loop, which dips down into the medulla. Now, the glomerulus and the proximal convoluted tubule, the PCT, are up in the cortex, and then we dip this structure here, kind of looks like a paperclip. It dips down into the medulla. We're going to be exploring that more in the next video. But for now, I think it's important to note that a portion of this thickens up. Basically, the one side becomes thicker, and then we get into the distal convoluted tubule. And then finally this empties into the collecting duct. Now the collecting duct receives filtrate from several different, we're going to draw 4 of them, several different nephrons. And let's label all of these parts. The proximal convoluted tubule, the nephron loop, the distal convoluted tubule, and all 3 of these, the PCT, nephron loop, and DCT, all 3 of those together make up the renal tubule system. And lots of things happen to the filtrate as it moves through the renal tubules, and it actually somewhat continues to be processed as it moves through the collecting duct. So again, we'll draw our collecting duct, and we're going to infer that there are actually several different units, several different DCTs. Not just the one we're drawing, but there are going to be several that are going to be emptying into this collecting duct. Let's go ahead and label that. So this unites the 2 stories. The collecting duct, those tiny little stripes that we saw in the medullary pyramids were called the collecting ducts. And what we're doing here is we're just looking at a real close-up view of them, and we're looking at the nephron that is attached. So what is a nephron? The nephron is kind of everything we're looking at here. It is the structural and functional unit of the kidney. At a microscopic level, it's made of the glomerulus, the glomerular capsule, the renal tubule system, and then the collecting duct. That is a nephron. So now what we're going to do is going to go ahead and draw filtrate, which we have to write kind of tiny here. And we're drawing this in orange, which is the same color that we drew the urine. So one of the ways to define filtrate, and maybe the most practical way to think about it in the first place when we're introducing the topic, is filtrate is basically going to turn into urine. So filtrate is future urine. In reality, filtrate gets processed a lot as it moves through the renal tubules and through the collecting duct. So it continues to be called filtrate all the way through all of these tubes. But it continues to be processed, and some things are taken out and some things are put back in. But whatever ends up at the end of the collecting duct is eventually going to be called urine. As soon as it moves through the renal papilla and then into the minor calyx, it is now urine. And I would argue that this basically means that as soon as filtrate leaves out of the glomerulus, it is outside of the body. It's going to be a theme today. So let's talk about the 3 steps of urine formation. The first of the steps is called glomerular filtration. It's kind of what what we showed in orange there. So we're going to draw a small glomerulus, draw a little glomerular capsule, and we're pretty much just going to draw that little first part of the renal tubule system, kind of a PCT, proximal convoluted tubule, but just we're going to simplify the story a little bit, so we're not going to draw all the convolutions and twisty turnies. We're just going to draw it straight. And so the first step of urine formation is going to be called glomerular filtration. And what happens in glomerular filtration is that filtrate leaves the blood. Basically, it is pretty much blood plasma is going to be pressed. Pressed is the important word here. It's going to be pressed out of the glomerulus. And so we're taking the blood plasma, whatever's going on with the blood plasma, if it's high in salt, for example, or high in glucose, or lots of water or something like that, then everything is going to be filtered out of the glomerulus and pressed out of the glomerulus and then pressed into the renal tubule system. And at this point it is called filtrate, and it's pretty reflective of the blood plasma with a couple of exceptions. So what we've done is we've taken something in the blood supply and we've pressed it out of the body, remembering that as soon as something becomes filtrate, it is destined eventually to leave the body. If it is not reabsorbed by the body, then it is destined to leave. So we've taken something from inside of the body in the blood and we've pressed it out. So this in versus out is going to be reversed with our next step. Our next stage is called tubular reabsorption, and this is the stage at which we take some of the items from the filtrate and we reabsorb them back into the body. They're going to leave the renal tubule system. They're going to get passed through the walls of the renal tubules, and they're going to re-enter the body. It's called reabsorption. So here we draw the simple little cue here saying out to in. So glomerular filtration, the first step, is where we went in to out. And then in tubular reabsorption, we're taking stuff from outside of the body and bringing it back on in. So let's be real clear about exactly how this works. This second stage here, it's not just that we reabsorb it back into the body. We reabsorb these substances, we'll talk about what they are in a moment, back into a blood vessel system, which we're going to just draw in purple. Just, it goes from red to blue, but it's helpful just to draw it all in purple. And what we're going to do is we're going to take our beautiful tubes and we're just going to surround them all the way up to the collecting duct with these purple strings. And this is a blood supply that's eventually going to be returned to the venous system and returned to the regular blood supply. All of these together are called the peritubular capillaries. It's right in the name. Peri meaning around, tubular meaning tubes, and capillaries meaning blood vessels. So peritubular capillaries surround these renal tubules and allow for the reuptake of all of those substances that are reabsorbed. And there's a specific type of blood vessel. There's a specific type of peritubular capillary surrounding the nephron loop, which is called the vasa recta, which again we'll talk about in the next video more. Well, at this point it might be useful to discuss what's actually in the filtrate. First of all, it's important to say that there are no proteins in the filtrate, and of course there are no cells in the filtrate. So the filtrate is fairly reflective of blood plasma, with the exception that there is no proteins. They are not allowed to leave the blood supply, at least under healthy conditions they cannot leave. And of course, the formed elements, the cells of the blood, do not leave the blood either. So other than that though, filtrate is fairly reflective of exactly what's happening inside of the blood plasma. For example, you may recall that blood plasma is high in water. About 90% of blood plasma is water. So of course there's going to be some filtrate in the water. There's also going to be a certain amount of sodium ions, calcium ions, other salts, other ions. And both of these substances, ions and water, will be selectively reabsorbed, basically dependent on which hormones are present or which amounts of hormones are present. For example, if you have a great deal of ADH, antidiuretic hormone, then water will be reabsorbed in stage 2, tubular reabsorption. If you have PTH present, parathyroid hormone, then you will be reabsorbing your calcium. And if you have aldosterone present, then you'll be reabsorbing sodium ions. So really, I think hormones are kind of the big picture here. If you have certain hormones present, these things will be reabsorbed, but if they are not present, it basically indicates that, okay, your body has plenty of, calcium at this time, or plenty of water, and we do not need to go to great efforts to retain these things back in the body. Next up, we're going to have some essential nutrients such as glucose and amino acids. These things are released from the filtrate, but man, we just went to a lot of effort to consume them and absorb them in the first place, so we do not want to let them go. You generally will not find glucose or amino acids in your urine. They are always reabsorbed, at least to the amount you can. Of course, if you have excess levels of glucose, for example, diabetes mellitus, the body cannot always reabsorb all of that, so you do lose some glucose to the urine. But generally speaking, if you do not have a disorder or a particular condition, then glucose and amino acids always reabsorbed in those proximal convoluted tubules, basically almost immediately after they were let go. So they're let go at stage 1, where the glomerulus presses out these fluids, but then immediately they are reabsorbed because your body doesn't want to let them go. But the opposite is actually true for the acid waste of metabolism. So your cells consume things like glucose and fats, and then they release substances like nitric acid or ketone bodies, for example. Just depending on which type of cell is metabolizing, they're going to let go some substances that usually are acid-based and oftentimes are based on nitrogen. Anyway, these acid wastes of metabolism, although I forgot to write it, go ahead and write this. They are always released. They are never reabsorbed. And so the acid wastes of metabolism are pressed out in that first stage of urine formation, and then they are never reabsorbed, because that's actually something that your body really wants. It really wants to let them go. You can't have acids floating around. It's actually quite caustic and dangerous. So acid wastes of metabolism are always released in the urine, never reabsorbed. I think this is a good place to summarize the 3 fluids that are found in the nephron region. Of course, we have the filtrate, which we're drawing in orange, which remains inside of those renal tubules. We have interstitial fluid, which basically surrounds all of the tubes, all the collecting ducts and so on. And we have the blood that is inside of those peritubular capillaries. Now, filtrate is considered outside of the body because it is eventually going to become urine. If it's not processed, anything that's left behind will leave the body. But both interstitial fluid and blood are considered to be inside of the body, of course. So this is one of the ways that we kind of convey information about this whole thing and say, when something is released into the blood, that means it's re-entering the body or reabsorbed into the body. But if it's released into the filtrate, then is outside of the body, it's destined to leave. I just personally think it's helpful to think of these fluids when you're trying to consider, where you are, trying to organize your thoughts about all of these things. There's quite a lot of details to come up, but basically coordinating in your own mind, organizing in your own mind where the inside of the body is and where the outside of the body is may help to keep things more organized in your thoughts. Right, so our third stage, I will just mention this, although we're not going to go into details today. The third stage of urine formation is tubular secretion. In tubular secretion, there are some cases where it's hard for the glomerulus itself to be the only way that things leave the body. So there are some toxins and there's some other substances that are kind of processed differently that are able to be moved, from the peritubular capillaries into the renal tubules. And so become part of the filtrate. And so this is a situation where you're taking something from inside of the body and pushing it out into the filtrate, which allows it to leave the body. And we're going to come across some examples of this. I'm not sure we'll specifically call it tubular secretion, but anything that is moving in that direction from the blood supply into the renal tubules, that would be tubular secretion. Right, so what we're going to do now is we're going to explore glomerular filtration a little bit more, and we're going to go into a little more detail about exactly how this works and some of the pressures involved and how things can be adjusted under certain conditions and so on. So we're going to draw ourselves our afferent arterial, which is thicker, our efferent arterial, which is thinner, and we're actually going to go a little bit more detailed this time and draw a glomerulus and draw some of the kind of the vessels of the glomerulus itself rather than just a tangle. The afferent arterial, we're going to go ahead and surround it with smooth muscle cells. The efferent arterial, same thing. This is an unusual capillary bed in that usually capillary beds are drained by venules, which are low pressure, but it turns out the glomerulus is both fed and drained by arterioles, which means that both tubes leading to and from are surrounded by smooth muscle cells, and therefore they are both able to vasoconstrict and vasodilate with very different effects depending on which one you're discussing. And look, I made a mistake, so I had to kind of cover myself and cover things over with black ink because I wanted to be really clear about this and I wanted to really correct myself. If you vasoconstrict the afferent arterioles, afferent means approach, yes? So we're bringing the blood supply into the glomerulus. If you vasoconstrict the afferent arterioles, this reduces the renal plasma flow. And that's a term you probably haven't heard before, but it basically just means the plasma flowing into the kidney, flowing into this little glomerulus here. And the opposite is true too. If you vasodilate the afferent arterial, you're basically bringing more blood in. You increase your renal plasma flow. It's a pretty obvious story here, but we're going to come back to it in a little bit. Just don't forget it. Now, the story of the efferent arterioles is a little bit different. Remember, efferent means exit. This would be bringing blood away from the glomerulus. And so when we vasoconstrict or vasodilate the efferent arterial, what we are doing is we are changing what's happening inside of the glomerulus. You are either giving more leave to the blood supply through the efferent arterial or giving less leave. If you vasoconstrict the efferent arterioles, what that does is it basically backs up blood. So you're tightening up the exit portal, and that means that the glomerulus itself is forced to push more filtrate out, so it increases the glomerular pressure. If you vasodilate, open up that efferent arterial, that means that more blood plasma is able to flow out of the exit portal, the efferent arterial, and therefore it reduces the pressure inside of the glomerulus. So I think the story of the afferent arterial, since it discusses renal plasma flow, is fairly straightforward. But you have to really kind of work your way around that efferent arterial and think about the backing up of that fluid and how that would change what happens inside of the glomerulus and how much pressure is exhibited in there, which we're going to talk about in a moment, called HPGC, the hydrostatic pressure of the glomerular capillary. Let's take a moment and take a chunk out of this glomerulus. We're running out of room up here, so we're going to put this down below. We're just going to take a closer up view at this microscopic structure. The glomerulus itself has some interesting structures to its walls. It is actually capillary of the body, so it is made of capillary material, simple squamous epithelium. In this case, the simple squamous epithelium has fenestrae, little holes. Remember that? Hole punches, tunnels leading straight from one side to the other. We discussed fenestrated capillaries before when we discussed three different types of capillaries. Fenestrated capillaries are these holes that basically punch straight through from one side to the other of that simple squamous epithelial cell. And just so you know, the fenestrae are about 70 nanometers in diameter, which is a little bit of an issue because it turns out, remember, going back up to the filtrate does not have proteins in it. But proteins are actually usually smaller than 70 nanometers. So technically, proteins could be filtered out of these fenestrae because they're, the albumin, for example, our major blood protein, our blood plasma protein, albumin, is only about 35 nanometers. So technically, if you just had open fenestrated capillaries, then the albumin would be leaking out all the time. And you can't have that. You can't have albumin being part of your filtrate. Albumin actually has to remain behind in the blood. This is quite important. So we have two other methods to make sure that structures like proteins do remain behind in the bloodstream. So the next layer we're going to be covering is called a basement membrane, and it's basically like a jelly that coats the outside of these fenestrated capillaries. So the fenestrated capillaries allow for things to be passed in and out, such as really small things such as solutes, water, ions, glucose, amino acids, and those acid wastes of metabolism. And those things are easily able to pass through the fenestrae, and probably also easily able to pass through this next layer, which is called the basement membrane. The basement membrane is full of negatively charged glycoproteins, and that repels the proteins. So the proteins that are in the blood plasma are usually taking on a bit of a negative charge, and therefore they will not probably pass very well through this basement membrane because it itself has a negative charge. So there's another stopgap. And then lastly, we have these podocytes, these beautiful, beautiful podocytes that I'm afraid I'm not drawing very well here, but a podocyte is, as the name suggests, a cell, C-Y-T-E, with foot processes. That's the podo part. So podocyte, foot cell. So the podocytes have these foot processes that in turn have these feather-like filtration slits that allow you to have a really small diaphragm, just a very small gap between, and these are actually covering all of the tubes of the glomerulus. And therefore, there's only about a 10 nanometer gap between these structures, and therefore anything larger than 10 nanometers is very unlikely to be able to leave out of the kidneys, outside of the fact, of course, that they are quite delicate, and if they become damaged, you might actually have the leakage of some proteins or something through these guys, these filtration slits of the podocytes. And so it's quite important that these beautiful, delicate structures remain intact and aren't damaged, for example, by a burst of blood pressure pushing out on them, for example. So there's quite a lot of work that the body goes to maintain the delicacy of these structures, because it's very important to maintain those proteins. So there are three things that basically are keeping certain structures inside of the glomerulus and not being pushed out as part of the filtrate. The fenestrae, the basement membrane, which is negatively charged, and then the foot processes of these podocytes. Now, we are going to, it looks like we're changing topics, but we're really not. We're going to be talking about net filtration pressure, and I'm afraid I'm going to have to use lots of initials here and state the words because I'm just not going to have room to write them all. So net filtration pressure is the amount of pressure that is involved in pushing out that filtrate. And it turns out there are some outward pressures and there are some inward pressures. The outward pressure, the main outward pressure, is going to be called HP sub GC, the hydrostatic pressure of the glomerular capillary. This is basically what we've been drawing in orange arrows through this entire lecture. It's the push. Hydrostatic means the press of water against a wall. So the hydrostatic pressure leading out from this glomerulus will press this filtrate out, HPGC. That is the outward pressure. But it turns out there's two inward pressures. There's quite a large pressure, which is called colloid osmotic pressure. We're going to abbreviate it OPGC, the osmotic pressure of the glomerular capillary. Now, the osmotic pressure of the glomerular capillary is the difference of this one's a little bit harder to explain, so let me take a moment to do it, and it's very important. It turns out that all of those proteins that were retained back in the blood, albumin being a big one here, this is actually the whole reason albumin exists, really. All of those proteins remaining behind in the blood pulls water back in. The concept of osmosis is the concept that water follows an area, like water flows across a membrane into an area where substances are more highly concentrated. So it turns out the fact that the filtrate has no proteins, but the blood plasma has a large number of proteins, means that a lot of fluid is actually going to be pulled back into the glomerulus. And this is called OPGC, osmotic pressure of the glomerular capillary. Quite difficult to understand, but it's so important that you do understand it. And then also there is a smaller pressure called HPCS, again a hydrostatic pressure, fluid pressed against a wall, of the capsular space itself. It turns out that glomerular capsule, there's not a lot of space between the glomerulus and the glomerular capsule. So as filtrate is pressed out of the glomerulus, some of the fluid is just pressed right back on in because that wall is fairly tight to the glomerulus. So the HPCS indicates that small pressure happening there. So the OPGC and the HPCS are both inward pressures coming from the colloid osmotic pressure because of the presence of proteins, and then that small amount of capsular space that kind of pushes fluids back in. Now the HPGC, the hydrostatic pressure of the glomerular capillary, is typically 55 millimeters of mercury, and we're going to be subtracting those inward pressures. The OPGC, the osmotic pressure of the glomerular capillary, is typically 30, and the HPCS, the hydrostatic pressure of the capsular space, is typically about 15 millimeters of mercury. So this leaves us with a nice healthy NFP, a net filtration pressure of 10 millimeters of mercury. So what? Who cares? Well, it turns out that your net filtration pressure contributes heavily and basically is the direct contributor to your glomerular filtration rate, your GFR, which is something that's actually measured by physicians when they're looking at your kidney health. It turns out that your GFR, the amount of filtration that is produced by your kidneys, is about 180 liters per day, which filters down to about 125 milliliters per minute. At least this is the typical for the males. Women tend to be around 100 milliliters per minute. So the glomerular filtration rate is heavily dependent on a nice, healthy net filtration pressure. And suffice to say, although we're not going to say much more about it, suffice to say that your GFR must remain relatively high, not too high, but relatively high. And so we put a lot of effort into making sure that your glomerular filtration rate is just about within the proper range. If it becomes too low, your kidneys will shut down, for example. So your glomerular filtration rate is a factor of your renal plasma flow. And remember, we mentioned this before. Renal plasma flow is a function of the vasoconstriction or vasodilation of the afferent arterioles. And renal plasma flow is also a function of your cardiac output. So if you can simply reduce or increase the amount of blood leaving the heart in the first place, you may recall all the way back to the start of this whole thing, we said about 20% of your blood supply goes to your kidneys. So if you manipulate your cardiac output, you can also manipulate your renal plasma flow. And your GFR is also a function of your filtration fraction. The filtration fraction is basically the percentage of plasma that comes into the glomerulus that's actually pressed out. So the amount, there's like a proportion there. Now it turns out that filtration fraction is a direct function of the efferent arterioles. The efferent arterioles either vasoconstricting or vasodilating. Remember that if we went back to look at those efferent arterioles, if we manipulate the diameter of those guys, you are manipulating the hydrostatic pressure of the glomerular capillary, the HPGC, which by the way is a super manipulatable number. Anytime something goes wrong, it's usually that number that is able to be changed very easily. So we can make quick changes to the efferent arterioles to change the way that our kidneys are behaving, and therefore any adjustments that have been made in the GFR can be fixed often by changing the diameter of the efferent arterioles, changing the HPGC, and then allowing for the net filtration pressure and therefore the glomerular filtration rate to go back to where they're supposed to be.